The planet Pluto, coordinated at the farthest reaches of our planetary gathering, is wrapped by a colossal number of cold heavenly bodies and space rocks inside the Kuiper Belt, a huge area of space beyond Neptune. Once worried as the 10th planet, Pluto gets its name from the Roman deity of the hidden world. At a critical crossroads in grandiose history in 2006, Pluto was renamed from its planetary status, mirroring the developing comprehension of our celestial neighborhood. Our ongoing excitement for the planetary gathering depicts a winding of prominent parts, including different space rocks, a select gathering of minor planets, and a record of only 8 traditional planets throughout mankind's set of experiences. Exploring many extended lengths of grandiose insight and assessment, our interpretation of these bodies has advanced significantly. We've acquired insights into their plans, strategies for acting, and likely conduct, painting a more nuanced picture of our cosmic environment. Yet, amid our growing knowledge, the appeal of our own existence continues to invite assessment and discovery. The James Webb Space Telescope, a zenith of modern galactic advancement, stands prepared to uncover a portion of these waiting experiences, including those involving Pluto. Notwithstanding its unobtrusive size and erratic orbit, Pluto has held an extraordinary place in the hearts of many for a long time, parading the distinction of being the smallest celestial object in our close planetary system. Pluto's renaming ignited a strong response from the public, highlighting the profound connection individuals felt toward this far-off body. However, scientific caution dictated that for an object to merit planetary status, it must stick to 3 key models: circling the Sun, having adequate mass to assume a nearly round shape under its gravity, and getting its orbit free from debris models that Pluto ultimately failed to meet with its lopsided orbital path. The term planet has undergone a captivating evolution throughout grandiose history. At first, it encompassed any large celestial body seen overhead, counting moons and asteroids. Pluto's discovery in 1930 by American cosmologist Clyde Tombaugh stirred global excitement, only to be followed by the discovery of similarly sized objects within its neighborhood, raising questions about its planetary status. Amid this discussion, Professor Mike Brown's critical revelation of Eris, a Kuiper Belt object practically identical in size to Pluto, further complicated matters and tested the conventional meaning of a planet. This led to a heated conversation within the galactic community, culminating in Pluto's renaming as a dwarf planet during the International Astronomical Union (IAU) meeting in Prague in 2006. Thus, Pluto's advancement from planetary status to a dwarf planet role serves as a demonstration of the dynamic nature of scientific understanding and the ongoing mission for clarity in the vast expanse of the universe. Following broad discussion, a changed meaning of a planet was proposed and put to a vote during the August gathering of the IAU, the body responsible for naming celestial objects and defining cosmic terms. In this meeting, the meaning of a planet was acclimated to include both Pluto and Eris, signaling a departure from the traditional understanding of what a planet is and reflecting a more nuanced view of celestial objects. Eris, previously known as 2003 UB313 and nicknamed Xena, was renamed after the Greek goddess of strife, mirroring the conversations and discussions surrounding its characterization. Mike Brown, a planetary researcher at Caltech whose work contributed to Pluto's renaming, gained widespread recognition for his endeavors, acquiring the epithet Pluto Killer via social media. This renaming prompted a brief correction of educational materials, including standards and textbooks, to reflect the new understanding of Pluto and Eris as dwarf planets. However, not all members of the scientific community promptly embraced the IAU's definition. Several planetary researchers, especially those focused on Pluto and similar objects, expressed concerns about the new rules, sparking ongoing discussions within the field of planetary science. These discussions broadened beyond scientific circles and into wider public discourse, raising questions about the possibility of exact characterization and the implications of renaming long-established cosmic terms. Notwithstanding these conversations, scientific inquiry proceeded unabated. In 2015, NASA's New Horizons spacecraft conducted a memorable flyby of Pluto, providing remarkable insights into this far-off world. The mission uncovered a dynamic and topographically active planetoid, with features like nitrogen ice plains and a conspicuous heart-shaped district, charming the public's imagination. As we consider these changes, it becomes clear that our understanding of the close planetary system and its constituent bodies continues to evolve. The renaming of Pluto and Eris as dwarf planets represents a milestone in our ongoing exploration of the universe, highlighting the complexity and diversity of worlds beyond Earth. As New Horizons ventured through space at an astounding pace of 32,300 miles per hour, it captured detailed images of Pluto's near side during its closest approach. However, due to the spacecraft's trajectory and the position of the Sun, Pluto's far side, often referred to as the dark side, remained hidden from view. Investigators carefully examined images taken by the spacecraft before its encounter to gather insights into this puzzling area. Notwithstanding the challenges presented by the limited extent of these pictures, they offered an outstanding degree of detail, allowing researchers to observe surface features down to around 1 mile across. This degree of clarity far outperformed past observations, including those from the Hubble Space Telescope, which orbits Earth. The examination of these images has provided new perspectives on Pluto's dynamic nature, with researchers exploring factors such as a potential subsurface sea and surface cycles. Later discoveries, such as the presence of ammonia on Pluto's surface and charming ice formations, continue to unveil the intricacy of this world. Richard Binzel, a planetary researcher engaged with the New Horizons mission, describes Pluto as the gift that continues to give, as it keeps astonishing analysts with its unpredictability. Before the New Horizons mission, the most detailed images of Pluto came from the Hubble Space Telescope, which revealed a world with distinct surface features. However, New Horizons provided essential close-up views of Pluto's landscape, including the striking heart-shaped area and the immense frozen plain known as Sputnik Planum. The revelation of Sputnik Planum's unusual arrangement, alongside Pluto's largest moon Charon, has sparked interest in its formation, with some researchers speculating that it might include a subsurface sea that has influenced its surface features. The presence of ammonia in the ice covering Sputnik Planum suggests geological movement beneath the surface, indicating a dynamic and evolving world. As researchers continue to investigate the data gathered by New Horizons, they are uncovering new insights into Pluto's complex and dynamic nature, extending the possibilities for future examination. The varied landscape on Pluto's far side, including hills, depressions, and fields, bears similarities to features seen on other celestial bodies with subsurface seas. While the far side of Pluto remains somewhat obscured, researchers eagerly anticipate future missions for closer assessment. The anomalies observed fuel speculations about Pluto's geological history and the role of its subsurface sea in shaping its surface. These revelations challenge conventional interpretations of planetary evolution and highlight the dynamic nature of distant worlds like Pluto. As New Horizons continued its mission, researchers speculated about the fate of Pluto's interior over the long haul. Radioactive decay inside the core could have produced sufficient heat to cause surface deformation, possibly leading to kinks or fractures like those seen on Earth. However, when New Horizons captured images of Pluto's far side, it revealed gaps rather than inevitable wrinkling. Pluto's surface indicated that it had partially frozen over the long haul. This massive fracture running along the near side of Pluto resembles Earth's East African Rift system, probably resulting from the freezing and expansion of a subsurface sea. The age of this fracture shows that the sea began cooling quickly after reaching the surface, potentially creating conditions favorable for the advancement of life. Additionally, the reddish hue of Pluto's surface, indicative of organic particles, suggests the presence of complex organic compounds. Laboratory tests have shown that such particles can form through radiation from solar wind or cosmic rays, highlighting a plausible scenario for their presence on Pluto. The revelation of ammonia-bound ice on Pluto's near side supports the idea that the dwarf planet might harbor rich organic compounds. While this doesn't imply the presence of life, it suggests that conditions could support life if they were suitable. Measurements from Pluto's far side have not only supported the mission's success, but have also led to the discovery of captivating topographical features like ice formations resembling tall structures. These developments, dispersed equally and rising forcefully, present a critical mystery. Spectral measurements show they are made of methane ice, forming a belt around the equator. However, their origin remains dubious, with speculations ranging from atmospheric hardening to disintegration by intense sunlight. Understanding Pluto's cold climate and landscape requires a careful assessment of its atmospheric conditions. Scientists are refining climate models to better replicate observed irregularities and aim to reproduce Pluto's atmosphere and surface conditions in laboratory settings. While the James Webb Space Telescope can't capture high-resolution images of Pluto, its longer wavelengths may reveal additional disclosures. As we continue to disentangle Pluto's secrets, we embark on a journey that reflects humanity's voracious quest for knowledge and the profound advancement of how we interpret the universe. The James Webb Space Telescope's capacity to accumulate and analyze infrared light offers a unique opportunity to study interstellar items, including those passing through our close planetary system. With its advanced capabilities, the telescope empowers researchers to dive into the secrets of these cosmic visitors, providing a clearer understanding of their arrangement and origins. This ongoing investigation highlights the significance of continued scientific inquiry in uncovering the mysteries of our vast and fascinating universe. The James Webb Space Telescope marks a new era in cosmology, bringing cutting-edge technology to the investigation of distant celestial objects and interstellar visitors. Equipped with advanced infrared capabilities, the JWST can notice vast phenomena that are generally imperceptible to conventional optical telescopes. This allows researchers to examine the early universe, star formation, and the composition of exoplanets with exceptional detail. One of the most prominent aspects of the JWST is its capacity to capture infrared light, which is vital for noticing objects that are too faint or too distant to be seen in visible light. The telescope's enormous primary mirror and refined instruments enable it to detect the faint thermal signatures of far-off worlds and other cosmic entities. This ability is particularly significant for studying the development and evolution of galaxies, as well as the atmospheres of exoplanets. The JWST's contribution to our understanding of the universe is evident in its ability to reveal complex insights about celestial objects. For example, its observations have provided new bits of knowledge into the structure and composition of far-off galaxies, shedding light on their growth and evolution over cosmic time. The telescope's observations of exoplanet atmospheres have moreover added to our knowledge of their potential habitability and the presence of atmospheric components like water vapor and methane. Interstellar objects unveil astronomical secrets. One of the most thrilling aspects of the JWST mission is its capability to study interstellar objects like Oumuamua. This strange guest from outside our close planetary group caught global attention when it was first detected in 2017. Dissimilar to any object previously noticed, Oumuamua showed a surprising elongated shape and rapid movement, prompting broad investigation and hypothesis about its origins. The JWST capabilities are expected to provide further insights into such interstellar items by investigating their structure and trajectories. Researchers hope to learn more about their origins and the processes that led to their ejection from their home star systems. This data can offer significant clues about the development and evolution of planetary systems beyond our own. Exploring Pluto and the Kuiper Belt, Pluto as a representative of the Kuiper Belt continues to be a focal point of scientific interest. The data from the New Horizons mission uncovered an abundance of information about Pluto's surface and its land features. As researchers analyze these discoveries, they plan to learn more about the processes that shape such far-off bodies. The JWST's observations could supplement and develop the findings from New Horizons by providing additional data on the composition and dynamics of Pluto and other Kuiper Belt objects. Understanding these distant worlds is vital for sorting out the history and evolution of our solar system, as well as the development of other planetary systems in the cosmos. As the JWST continues its mission, groundbreaking disclosures are expected that will advance how we might interpret the universe. The telescope's capacity to see in the infrared range opens up new opportunities for exploring previously subtle aspects of space, from studying the earliest galaxies to examining the atmospheres of exoplanets and interstellar guests. The JWST is poised to make significant contributions to cosmology. The continued investigation of Pluto and other heavenly bodies will additionally enhance our understanding of the solar systems beyond our own. By combining data from various missions and telescopes, researchers can build a more comprehensive picture of the universe and its many wonders. In conclusion, The James Webb Space Telescope stands at the very forefront of galactic research, offering extraordinary insights into the universe. Its cutting-edge technology and capabilities promise to unlock new secrets and expand our understanding of the cosmos. Preparing for future discoveries and broadening the horizons of human knowledge, the exploration of Pluto and the Kuiper Belt provides invaluable insights into the formation and evolution of our solar system. This distant region is home to a variety of objects, including icy bodies and potential dwarf planets, which serve as remnants from the early solar system. Understanding the dynamics of the Kuiper Belt enhances our knowledge of planetary formation processes and the migration patterns of celestial bodies. Recent research has focused on the geological processes at play on Pluto, suggesting that its surface is not static but rather dynamic. The presence of nitrogen glaciers indicates that the dwarf planet experiences climatic changes that could affect its atmosphere and surface features. This highlights the importance of studying Pluto's seasonal cycles, which may reveal more about its atmospheric composition and behavior over time. Additionally, the potential for subsurface oceans in celestial bodies, like Pluto, opens up intriguing possibilities for astrobiology. Investigating these environments may help scientists assess the habitability of other icy worlds in our solar system and beyond. As missions to the outer solar system continue to evolve, future explorations may uncover further mysteries, advancing our understanding of not only Pluto but also the fundamental processes that govern planetary systems across the cosmos.